Last class, we talked about damp-driven pendulum, and we discussed how to create a phase space plot, use a phase space plot that describes fully the motion of the damp-driven pendulum. And we looked at some examples of the phase space plots from the simple pendulum with no damping and no driving force to a damped pendulum with underdamping, overdamping to a driven pendulum, where in the region of strong driving, large driving constant, we discovered bifurcation and we discovered chaos in that region. In today's class, we're going to further talk about damped-driven pendulum. We're going to introduce Poincare plots for the damped-driven pendulum. And again, we're going to look at Poincare plots for the simple pendulum with no damping and no driving force, and a damped pendulum with underdamping and overdamping, and a driven pendulum, and again explore bifurcation and chaos. The ultimate plan for today's class, the ultimate sort of goal, is to make a Feigenbaum plot lightly made for rabbit populations or human populations based on logistic equation. We're going to make a Feigenbaum plot, or what we might also call bifurcation plot, for the damp-driven pendulum. In both cases, whether it's the rabbit population or the damp-driven pendulum, the Feigenbaum plot or bifurcation plot is a very good way, very nice way of representing the landscape, the world of bifurcation and chaos. So that's our goal. One other remark, in the last class, we approached chaos by varying the frequency of the driving force at fixed amplitude of the driving force. In today's class, we're going to do the reverse. We're going to approach chaos by varying the amplitude of the driving force, and we're going to stay at a fixed frequency. So chaos bifurcation is a feature of strong driving forces, and chaos and bifurcation occurs at over a landscape, a spectrum of driving force amplitudes and driving force frequencies. And so that's a kind of two-dimensional world of the amplitude and frequency of the driving force. And as I say, in the last class, we approached the chaos from the perspective of changing the frequency. In this class, we're going to approach the chaos from the perspective of changing the amplitude of the driving force. Just two different ways we can get there. So this slide just introduces the Poincare section plot, call it, and its relation to the phase space diagram, what we meant last time. So the phase space diagram very clearly shows the motion of the pendulum. So it literally tracks the path, trajectory of the pendulum in this phase space, which is this space of the pendulum angle and the pendulum angular velocity. So phase space trajectories are path trajectories in that theta omega space. For the simple pendulum, the phase space trajectory is just a circle or ellipse or oval, depending on whether you have large or small amplitude swings. For the damped pendulum, the phase space diagram can look like a spiraling inwards, showing oscillating and exponentially decaying motion, in showing the path of trajectory of the pendulum. In the case of damp-driven pendulum with chaotic motion, the phase space diagram becomes very chaotic itself. So in the sense it clearly displays the chaos that's going in on the chaotic motion, but it is a chaotic plot that is hard to, it's kind of overwhelming in the content, sort of too much in the content. The Poincare section plots are an alternate way of looking at that chaotic motion that kind of helps us to bring a bit of order, a bit of understanding to the chaotic trajectories. The key thing is that in the phase space plots, we're continually monitoring the angle and the angular velocity of the pendulum over all time, continuously as a function of time, and develop the path of the trajectory. In the Poincare section plots, we actually only monitor the angular position and the angular velocity of the pendulum periodically, where the period is either the period of the natural oscillation of the pendulum or the period of the driving force that's acting on the pendulum. So we only look with the at particular moments in time, so discrete moments in time, that correspond either to the natural period. So we look once every natural period. So we wait one cycle worth of time and look at the coordinates of the pendulum, wait another cycle of time, look at the coordinates of the pendulum, or we do it with the driving period. We'll look at the pendulum's coordinates every driving period, the first driving period, the second driving period, and so on. Yeah.
So the independent variables, which period we're looking at, like the first, second, third, fourth, fifth?
The independent variable is, I would say, is still time, right? Just like in the phase space plot, time is the independent variable, and theta and phi, the angle and the angular velocity of the dependent variable. It's just we're choosing to plot theta and phi continuously versus time in phase space diagrams. We're choosing to plot theta and phi periodically in the Poincare section plots. So it's the same dependent variable in both, independent and dependent variables in both cases. It's just that, that choice is about at what times we're plotting the trajectories or the path. A couple of words about the Poincare section plots. These will become more obvious when we start looking at examples. So one is I labeled here this starting cycle, and one is this cycle period. Actually, I haven't mentioned the first one, but I did mention the second one. Often, in making Poincare section plots, we won't start plotting the position coordinates of the pendulum at these particular intervals, these particular periods, from starting from time zero. We'll wait to some time has elapsed, so the transients have died off, and then start making the plot. So we'll often introduce a delay before we start creating the Poincare section points that go in the Poincare section plot. So that's one point, and we'll see why we do that. And then the other point I was making, we say we're going to plot the data every period of the pendulum, once every period of the pendulum, but there's two periods associated with a damp-driven pendulum. There's the period that corresponds to the natural frequency. There's a period that corresponds to the driving frequency. And so we'll make choices about which period, driving period or natural period, is relevant to our particular plot. Okay, so if you want to imagine Poincare section plot, imagine you've got a pendulum in the room, hanging there, swinging to and fro. We switch the lights out, we can't see the pendulum. And then we put on a stroboscopic light that flashes with the period, natural period of the pendulum, or it flashes with the driving period of the driving force. And so you occasionally, for an instant, see the location of the pendulum. You see the coordinates of the pendulum. And that's a Poincare section plot of the pendulum with that stroboscopic recording of the position and the velocity of the pendulum. Okay. Now, one of our goals is to, from the Poincare section points, actually create a Feigenbaum plot that we met in one of the early classes that we might also gets called a bifurcation plot. And on this slide, I just reproduced a couple of plots from the early class, and we looked at the evolution of rabbit populations or human populations, generation by generation, over some long period of time, and from which we made a Feigenbaum bifurcation. And I just wanted to point out that in looking at the rabbit population versus time, looking at the human population versus time, we were looking at the rabbit population, the human population from generation to generation. Each generation, we recorded the population of rabbits or the population of humans. And that's like, again, stroboscopically plotting the function, the dependent variable versus the independent variable. And so the population versus time, we're looking at it once every generation. So that really was like Poincare point data from which we made a Feigenbaum or bifurcation plot. So that might be helpful to remember that we've already done, in a sense, in a way, these Poincare section points, these Poincare section plots, when we talked about the biological evolution of the rabbits or the humans, because we were looking at periodically there, we were looking each generation, just plotting the data to each generation. That's the only reason I showed this plot. Don't worry about the details on this slide. Okay, wanted to show the reminder, just to remind us of the language we're working in. We're solving this differential equation here, second order differential equation with restoring force, a damping force, and a driving force that produce three corresponding accelerations, restoring acceleration, damping acceleration, driving acceleration. That's what you see in these forms of the equations. These are the angular acceleration contributions that add up to create the total angular acceleration. There's basically four parameters in this differential equation. We're in a world of a kind of four parameter space that we can control and we can adjust by choosing our pendulum. There's the natural frequency that has one parameter. There's the damping constant, the second parameter, and then there's the driving force coming with two parameters. Its frequency and its amplitude. So these two parameters here. So that's the space in which we live. And by setting one or other parameters to zero, we could get rid of the driving force, so we can get rid of the driving and the damp force and get to simpler situations. Okay, so I'm gonna go to my code, I think, and we're gonna make some plots of pendulum motion. I'll start with simple pendulum motion without a driving force, without a damping force, and return on the damping force. We'll look at that in the cases of under and over damping. Then we'll turn on the driving force, and then we'll work towards chaotic motion. I'll also build up the Poincare plot. I'll show you how it's related to the phase space plot in my code. So that's the plan here. In the slides, just so you know, I've kind of cut and paste the results of my program for phase space and Poincare section plots for all the different oscillations that we're going to look at. But I won't work off the slides, I'll work off the program. Okay. This is a code in my Physics 508 directory where generated the solutions of damp-driven pendulum, made phase space and Poincare section plots for this. And let's just walk through this. Obviously, we'll make it bigger. A lot of it is a copy from our last class where we made the phase space plots, and I'm just adding the Poincare plots. So a lot of it I'm going to skip through, but just as a reminder, there's a couple of user functions that I have always been defining over the last handful of classes that define the ordinary differential equations that we're solving and define the Taylor approximation method that we're using to solve them. So this pendulum user function is my definition of the ordinary differential equations describing the system. And this RK4 function is that fourth order Taylor approximation to the solution of the differential equation at a future tick based on the solution at a current tick. Okay, nothing new there. Nothing mostly new here, I think. These are the parameters of the pendulum. I'm going to start with a pendulum that has a natural frequency, which is square root of G over L of 1. I'm going to have its length be 9.8 meters in the Earth's gravitational field at 9.8 meters per second squared. That's only going to know what the natural frequency is, 1 radian per second, or a period is 2 pi seconds. So swing very slowly. You know the 6 seconds for complete period. I've got here the damping force switched off, and I've got the driving. So my damping constant, driving constant, beta and gamma are 0. I've got to set up my initial conditions from which I swing the pendulum. I've always been picking these initial conditions just as an example, but they are just an example. So I've just displaced the pendulum away from the equilibrium by about 5 or 6 degrees, but I've released it from rest. So theta naught is 0.1 radians and under theta naught is 0. I think this bit's a little bit new. I'm going to make plots of the phase space and Poincare section plots for a certain number of periods of the natural pendulum, natural periods, if I don't have a driving force. And I'm going to make the same sort of plots, but of a certain number of driving periods of the pendulum if I have a driving force. So I've got an if and else there. If I don't have a driving force, I'm going to make the time range an integer number of natural periods. If I do have a driving force, I'm going to make it an integer number of driving period. And that's because, well, if you don't have a driving force, well, you've got to use the natural period. If you've got a driving force, you're more interested in the driving force, so you pick the driving period. So that's what's done in these lines here. Is this big enough at the back? Or should I make it larger? Nope. So having said all that, in periods is going to be the time range of my plots in units of periods. But that might be natural periods or driving periods, depending on whether I have a driving force or I don't have a driving force. Number of times is that maybe a better word would have been number of ticks. I mean, number of times is the number of ticks of my proxy for continuous time, which is a finely spaced discrete time. So this is the number of ticks in the time range, and this is the number of periods in the whole time range. This is where I make the time range either in terms of the natural frequency, or here is the driving frequency. And then downstairs here in this section of the code, this is where I generate an array that are my proxies for the independent variables. So I've got a one-dimensional array that's my proxy for time. I got a of size n, the number of ticks, and then I've got a two-dimensional array, which is my meta variable that contains both the angular position and the angular velocity. That's an array of size, the number of ticks, times 2, because it contains the meta variable that contains the angular velocity and the angular position. So I define those and I set the very initial values of the position and the velocity to be the initial coordinates that I set up here for my pendulum. So that's the first element of the zeroth column, corresponds to theta, and the first element of the first column corresponds to omega. Yes.
You set the driving frequency in unit of natural frequency.
Yeah, I did. Actually, that this comment here is completely wrong. So because this is not a magnet, this is the driving this should be the driving frequency. As you say, in units of natural frequency. Okay. I think we got through. Oh yeah, we walked through the definitions of the independent and dependent variables. The next stage in the code is finding the solutions to the differential equation. So actually, that part of the code is just these two lines. I'm just going to walk through my independent variable. This is going to be the index of the clock ticks, my independent variable. And as I walk through the independent variable, I'm going to take the current values of the dependent variables, the theta and the theta and omega, and I'm going to calculate their values in the next clock tick. And in that way, out of just knowing those initial conditions, I'm going to reconstruct the entire trajectory of the pendulum through space and phase space. So I've done that there. After finding the solutions, just for convenience, really, rather than anything else, I'm going to strip out the theta into a one-dimensional array and the omega into a one-dimensional array for the plotting that I'm going to do. So those are these two slicings that are going on here. Just for convenience, I'm not going to work with the n/2 array that contains both coordinates, the sort of meta-dependent variable. I'm going to work with two individual arrays that contain the individual coordinates. This was something that we met in the last class where I said, if you loop the loop and you keep adding positive 2 pi's or negative 2 pi's, depending on whether you're turning clockwise or counterclockwise, you can loop clockwise or counterclockwise. I'll just also keep a variable that is that angle modulo 2 pi, i.e. where the pendulum is around like the clock face, with 0 being the equilibrium and minus pi and plus pi being the two extrema of the pendulum's motion. So this is just basically dividing by 2 pi to get this theta modulo 2 pi. So these are my solutions that I'm going to work with. And then I'm going to come down to plotting. And I'm going to make a, just remind myself what I do. I'm going to make a few plots down here. Some of them are old ones and some of them are new ones. So my theta n and my omega n are the solutions to the differential equation. Those represent the phase space, the trajectory of the particle. So if I wanted to plot the phase space trajectory of the particle, I could just plot the values of theta n and omega n versus time. We did that in the last class. But I also want to just plot those coordinates, theta and omega, stroboscopically once every period. Once every, in this case, natural period is the only period I got. And so I'm going to set myself up with a couple more variables that are now me to make the strip out the Poincare section, which are the coordinates of the pendulum every natural period. And to do that, I'm defining these two quantities here. So this is this quantity n section. I'm sure that's a great name, but the section is for Poincare section. It's the number of clock ticks from one natural period to the next natural period. So there's a certain number of clock ticks between periods, and this is that period, and it's only at intervals of those clock ticks that I want to look at the coordinates of the pendulum. So that's going to be helpful when I slice out the positions of the pendulum at these natural period intervals. This is ticks in in one natural period, and then this in transient. It's not really relevant for the case of the simple pendulum because I don't have any transients, but it will be relevant for the case of the driven pendulum where I do have transients. This is just a number of clock ticks that I'm going to wait before I start making Poincare section points, my Poincare section plot. So I'm going to wait. Remember, there were 16,000 clock ticks in my entire time range. I'm actually going to hang out for 10,000 of them and not plot anything in the Poincare section plot, and only plot make the Poincare section points and plots for the last 6,000 of those 16,000 ticks. So those are just two parameters that I'm defining that are going to be handed down. Okay, I'm going to make 4 plots in a 2x2 array. So I'm defining that fact here. The plots, let me just show you what we'll go through some details. Yeah.
Like the period, the number of ticks period, or
the period was let me go back up to
this is like set it to 4.
So I'm dividing, I think I'm dividing this number by this number. So I'm dividing the total number of clock ticks in the histogram, which I defined already, by the number of, in this case, natural periods in the histogram. So this will give me the number of ticks in one period. So think of the numbers. This is 16,000. I'm going to divide it by 40. I'm going to get 400. That's the number of clock ticks that corresponds to one natural period. Does that make sense?
But how do you know it's 40?
It's because the time is 80 pi.
I mean, I'm just choosing to make the time range. This is my definition of the time range here. Maybe I wasn't clear about that. But I'm defining the time range to be 2 pi over the square root of g over l. That would be 2 pi over the square root of gl is the natural period.
Yeah.
So I'm taking the natural period and then multiplying it by the number of periods to get the full time range. So that makes this equation here makes the full time range 40 natural periods. This equation here, so that equation is executed if there was no driving force.
So it's like you're building like from the natural frequency to how many time ticks you're going to.
Yes, yeah.
Not the other way.
Yeah, I defined how many periods I want, and then I build everything out of that. I want 40 periods, I'm going to build periods out of that. Yeah.
Yeah, I was just going to say, all the alignment for this in particular, you're supposed to do for 80 pi as the time. So 40 just that 80.
Yeah.
That's what I was saying.
And this is just, as I was saying, I want it to be 80 natural periods if I don't have a driving force, and so 40 natural periods if I don't have a driving force, and 40 driving periods if I do have a driving.
Is it like more intuitive if we just give whatever total time takes and we just count how many we still like report every period, but then we count how many time takes are there like for a natural period?
Yeah, that's a very good question. If I understand your question, is why don't I just pick a time rate, like say 100 microseconds?
Yeah.
And then just pick out the points that are that correspond to one period. The problem, and I'm pretty sure that's the way I originally went to do it. And the problem I found is that you're not guaranteed if you just pick a round period, right? I pick 100 microseconds, some convenient number. You're not guaranteed that the number of ticks in one period is an integer number. And so the number of ticks that you could get an approximation for the period in ticks. And then what happens is it's like supposing you're strobing a simple pendulum. You're strobing the simple pendulum, but not quite at the right frequency. And so you create a unreal effect, right? The pendulum starts to walk around in phase bend. So that's why I kind of did it this. Well, I think you're right. This seems like an awkward way of doing it. Why did I pick the number of periods? It's because of this. I wanted to make sure that my period is a whole number of clock ticks. Okay, I was going to show you the plot, and then walk through how I made the ingredients in the plot. So I'm making 4 clocks, but the bottom 2 of them are just the old dependent variable versus time. So theta versus time on the left and omega versus time on the right. So those are the things we're very, very familiar with. Upstairs here on the left-hand side is kind of a traditional phase space and Poincare section plot. And on the right-hand side is a three-dimensional Poincare section phase space plot, where the extra dimension is the time dimension. That's the vertical dimension in this plot. So the one on the left, which is just angular velocity versus angular position, is the horizontal plane of this. Everything basically compressed onto that plane. So you don't see time. There's no time axis on here. This plot is on the right, it's just the left-hand plot, where I've added a third axis, added how the phase space trajectory and Poincare section points are evolving through time. Anyway, I just wanted to show you that on the plots that I'm going to make all the time, I've got the old-fashioned theta and omega versus time at the bottom, and I got on the top row, I've got versions of phase space plot from last class and Poincare section plot from this class. But let's go and just see how I make them. This is for a driven pendulum, so don't worry about what that looks like. Okay. So at the bottom here, let me make this a bit larger. These two plots, which are in row number 2, are the old dependent variables versus time plots. I won't say any more about those. This plot here is the traditional phase space plot and the traditional Poincare section plot. These two calls to plot create, the upper one creates the traditional phase space plot, and the lower one creates the Poincare section plot. What is the phase space plot? It's the theta coordinate versus the omega coordinate. So theta, it's a plot of theta and omega points versus time. And so I'm just plotting for the phase space here. The theta and omega points for all the times after this transient time. So I am applying this cut to remove any transients. That is not relevant for a simple pendulum, but will be relevant for the damped pendulum. But I'm basically plotting all these points of theta and omega. So this line here creates the phase space plot, and we did this in the last class. And probably the only thing I've done differently in this class is that I've removed with a slice the early time region, the first 10,000 ticks, and only plotted the later time region, which is the 6,000 final ticks. Then the other thing I added to the plot looks almost the same. It's the same theta versus the same omega. So that's exactly the same. I've got slicing again, so I'm slicing off the first with the end transient. Where is it? I'm slicing off the first 10,000 points. But I'm also, with this third argument here, the arguments in slicing are your first element that you want to slice from, the last element that you want to slice to. So I'm slicing from end transient. That's where my data will begin. I'm slicing to the end of the array. And then the third argument is the period of your slicing. It's how many do you want to slice? Get every tick, or do you want to get only every nth tick? So that third argument in section is saying I only want to plot every nth tick in my data. So that's the meaning of that argument. It's exactly what we want to do with the Poincare section plot, where we only want to plot points that correspond to intervals of either the natural period or the driving. So that's how I made the left-hand upper plot, which is the phase space plot, and you will have the Poincare section data. We'll look at it in a moment. I just mentioned, I'm not going to worry about the details of the three-dimensional plotting. I just wanted to show you it in case it helps to picture what's going on. But this little section here was to make the upper right-hand plot, the three-dimensional plot. This is the one that, if we look at the cause to the plotting, they have three arguments. So they have theta and omega, like a traditional phase space plot, but theta and omega are time, the dependent variable. And time is the vertical axis on these plots. And that's true for the phase space diagram. I did it, where I didn't just plot kind of stroboscopically the phase space points. And then the Poincare section version of the Poincare section plot is this region here. So it's the same variable, theta, omega versus time, but now I'm applying the transient cut, and I'm also only plotting points every n section points, where n sections is the natural period. Okay, let's run that. And this, I'm going to make this smaller. Look, this is just, yeah.
It's a very basic question. Is that what the double colon is doing with the these brackets? Is cutting?
Yeah,
that?
yeah. Let me just be completely clear about that. Then we'll send it right. Can you see this?
Yeah.
So this splicing is specified in the square bracket. There's, for my Poincare section plots, there's two colors for this one-dimensional array slicing. The first number is the index of the array where you start. So that's why I put n transient. The second number is the index of the array where you would stop. But if you leave it blank, you run to the end of the array. So I'm going to the end of the array. And then the third index is the step size with which you walk through the array. So again, if you leave that blank, it will treat it as one. Or if you would omit it, it will treat it as one, which is how we've used slicing in the past. But if you specify a step size, it will only plot the, it'll only slice out the data every step interval. So it's a very useful trick for making these Poincare section plots. Downstairs here, I've lost the scale on it, but this is theta and this is omega, and you just see the periodic oscillations, right? This is the phase space and Poincare section, traditional phase space Poincare section plot over here on the left-hand side upstairs. This circle or the ellipse is the phase space trajectory. Remembering, if you've just got a simple pendulum where there's no damping and driving, the pendulum just goes around a elliptical path in phase space, or an oval path in phase space, where it just repeats and repeats and repeats, running over itself time and time again in the phase space trajectory. This purple point up here, that's actually many purple points. That's the many purple points that we're plotting when we make the Poincare section points. And what we see is, for a simple pendulum, then the Poincare section plot would just show a simple single point, because every time you look at where the pendulum is, you're looking at the pendulum's coordinates with a period that's the natural period, you always see it at the same location in phase space, in theta and omega. So we just see this simple point in theta and omega. This is just to maybe make you believe that that's the case. So the horizontal plane here is the same theta and phi as on the left-hand side, but vertically is time. You see here that this oval or circle or ellipse is actually kind of like a spring stretched out over time, helix. So that's the time evolving. So you see all the individual parts of the pendulum. These blue points, I applied a transient. I only applied the Poincare section points after the transient, so they don't stop until like 10,000 ticks. So they're starting up here, and you see that each orbit phase space here, we get successive points that are the corresponding Poincare section points. Yeah.
I'm just wondering, so is it more illustrative to have to use the modulo data points for theta because like I mean I understand that if you make it go past 2 pi that it'll be like basically like a line with slope of omega.
Yeah, so right now I'm not plotting the modulo data because it's irrelevant for the natural period. If we go to, and I've commented out the lines that plot the modulo data.
Okay.
I think when we go to the driving force, you could do either, and one may make sense, or the other one makes sense, depending on whether you care about whether you loop the loop or whether you didn't care about whether you loop. So I don't think there's I don't think there's a statement you should use one or the other. You should use one or the other based on what your interest is, I think.
But it should be like a 3-dimensional, like your position in space versus time. Is that it should still be like having a 3-dimensional thing like that.
So this is what I would normally call phase space plot and the Poincare section plot. This is, I don't know what the name of this is. This shows you also the dependent variable. So it's just meant to be an illumination of this, if that helps. You might have noticed, so we said that this Poincare section here should be the same location, each theta and phi, each period. But if you look at that purple point, it's not quite a point. It looks like it's smeared out a little bit. And that's because we're plotting each natural period calculated by the square root of G over L. But that's, that assumes that the angle is small enough that you start the pendulum from use small angle approximation, that the period is exactly G over L. But we started at a pretty small angle that was about 6 degrees, but it's not small enough that that the frequency of that pendulum is exactly the natural period given by the square root of G over L. So that's the reason that this is smeared out a little bit here. I can exaggerate it. If I was to go back up, if I can. If we were to make this 1, so release the pendulum from 57 degrees, then you see a really exaggerated effect where we're nowhere near the frequency of the pendulum is nowhere near the natural frequency square root of G over L based on small angle approximation. And you see all these Poincare section plots. So these points are evolving around the trajectory. If I had made it really small displacement, where's the displacement? then this case, right, this much 10 times smaller than the original displacement, this does indeed look like a single point, because now we've released it from half a degree, and now it is extremely close to the square root of G over L natural period. Okay, let me show you a couple more cases, and then we'll get quickly onto the driving case, which is the most interesting one we want to look at. I'll put back this to kind of the nominal 6 degrees. We're going to switch on a underdamping, so beta of 1, 0.1. And just take a quick look at what phase space looks like for that. Well, downstairs here, we're familiar with the fact that under damping, the oscillations will die away, but the time constant is 1 over beta. And we see that here oscillating, but exponentially dying away. This is what the damping, the under damping looks like in a phase space plot. The free, where it spirals into this point here that we might call, and later we'll call a tractor. The pink points just represent a trajectory towards that attractor. So the phase space points themselves are along a trajectory. They have approximately the period of the natural period and the pendulum period are pretty close, not exactly the same. So they sort of follow a straight line point. There's just the amplitude of the oscillations decrease over time. So that's kind of the Poincare section trajectory to the equilibrium. And here you kind of see it in 3-dimensional glory, or wherever theta phi versus time vertically. The red line is the phase space. These Poincare section points here, the plotting are just the ones after the transient. So it didn't make much sense here, actually, because the oscillations have died away. Okay. In the notes, I show you critical damping. I also show you over damping. Let's get on to the case of a driving force and talk about the situation with different driving forces. So this is just a matter of choice, an explanation. But when I started to switch on the driving force, I did all my simulations with a damping constant of 0.25. I'm going to make this bigger. So still under damped. I've got a damping constant, to explore the driving force, because if I'm infusing energy with the driving force, which is what I'm doing, the oscillations would just get bigger and bigger and bigger and infinitely large if I didn't have some damping force to also dissipate the energy. So there is an energy balance that's going to be going on when I get to steady state, in that the energy balance is that the infused energy from the driving force is being dissipated equally by the damping force. So that's how I can get a steady state condition. If I didn't have a damping force and I had a driving force, I wouldn't get a steady state, because I keep on adding energy to the system. And so I keep on getting larger and larger amplitude oscillations. Anyway, I got a damping, and I'm going to add a driving force. We said this time I'm going to vary the driving force. I'm going to vary the driving constant that sets the scale of the driving force, and I'm going to keep the frequency. I'm going to keep that frequency to be constant. And as I say, that's the reverse of what we did in the last class, where we kept the driving constant, and we kept the varying the frequency. So this case here is this is what you call this weak damping. The driving constant is 0.1. So it's 0.1 of the driving force is 0.1 the size of the gravitational force. So that's weak damping. And if I make the driving constant order 1 or bigger, then that would be strong damping, where the driving force is as big or bigger than the gravitational force. We'll start with weak damping. Why is it different? I have no idea what's doing that. So I won't keep showing you these two plots, the theta and the omega versus time, but we've met those before. This is the case of the phase-space plots and the Poincare section plot. Now we've got a driving force. Let me show you one thing. And it says here that we met before. Right? So now we've got driving, damping, and a pendulum. There is a transient period. Doesn't last very long, but there is a little transient period in here, right at the beginning. The first few cycles are different from the later cycles. So that's the transient period in this case of weak damping. That's a case where the oscillations are more complicated. There's some more complicated function of the natural frequency in the driving period. But if we wait a few cycles, in this case of weak damping, after a few cycles, what we see is the oscillations are just at the natural period, the driving period. So we have taken a big step here. We've gone from oscillations occurring at the natural period to now all these oscillations are at the driving period, which was 2/3 of the natural period. So that is a change. Now, upstairs here on the left-hand phase space plot, I'm only plotting the phase space once we're in the steady late time steady state region. I'm only plotting the Poincare section point in this late time steady state region. So things are very simple in there. In the three-dimensional phase space Poincare section plot over here, I actually plot the phase space from time 0. So you see that transient in this first kind of path around here doesn't look exactly like the other paths of the pendulum through the equilibrium as it swings backwards and forwards. So you can see the transient in there. But this is what the Poincare section and phase-space plot for damp-driven pendulum look like in the case of weak damping. What you will see is that after you get through the transient period, where the oscillations are a bit more complicated, you just get into a simple period where the simple region where the pendulum is oscillating with the driving period, not the natural period. And the amplitude of the oscillations is determined by the driving period, the driving constant, and the damping constant, because they're determining this sort of balance between the infusion of energy from the driving force and the dissipation of energy from the driving constant. So the fact that the motion is staying the simple repeating periodic motion has at its heart, though we don't see it yet, the fact that the energy being infused is equal to the energy being dissipated. So we get this nice oval to the path here. We get a single point when we look at the Poincare section. Because this motion is just repeating, but this point is being plotted every driving period, not every natural period. So it repeats every driving period. Let's turn up the driving constant. So I'll go up to, let's go up to 0.9. So now this is basically strong driving. And I think I'll focus on the top two plots. Only the one on the left and the right here shows the transient. So this funny curve in here, that's the transient. The one on the left only shows the steady, what's happening steady state. So what's new here? I would say we still have a steady state where the pendulum is periodic in its motion. We can see that because there's in phase space just this green oval, so the pendulum is repeatedly going around this green oval. We can see it because there's a single purple Poincare section point, which is actually many points plotted on top of one another, so the motion is repeating. We can see that this is a nonlinear differential equation due to the large amplitude of the motion, because this is not a simple circle or ellipse. This is a periodic oscillation, but not a sinusoidal oscillation that's going on here. That's a consequence of this is a large driving force creating large amplitude motion. Look at the radians here, from -3 to +3 radians. So we're nearly looping the loop, but not quite looping the loop. So it's periodic motion under the driving force, but it's not sinusoidal motion under the driving force. The weak driving force gave us periodic and sinusoidal. Okay, let's jump to a couple more cases. I'm just going to change the constant here. 1.05. What happens there? Looks pretty similar on the left-hand plot. Looks significantly different on the right-hand plot. So in this case, when we set the pendulum going, it initially, in the transient period, there was a longer transient period, it was a more complicated transient period, and in that transient period, we loop the loop. You see the theta coordinate, where this axis here on the right-hand plot is theta coordinate. The theta is going away from 0 to negative value. So it's loop the loop. We see that on the theta coordinate over here on the left-hand plot. It's no longer centered on an attractor at 0 radians. It's centered on an attractor that's now at 2 pi radians. So this is the effect of looping the loop. But once you get through that transient period in which you've looped the loop, you reach a kind of steady state motion again, where the pendulum is moving periodically, and but not sinusoidally, and it's just repetitive motion of the pendulum under the driving force. So in that steady state time, again, the green line, the phase space is a kind of funny shaped oval that represents repeating motion. The Poincare section points are just one dot on top of one another, one purple dot on top of another purple dot, saying that every driving period, the pendulum has the same coordinate. So it's periodic motion. It's not sinusoidal motion. This is not a nice smooth ellipse. But it is clearly periodic motion. You can see that in the phase space plots, in the Poincare section plots. Okay. Let's go to this was 1.05, so just fractionally above the gravitational force. I'm going to go to a couple of special cases now that hopefully work. So this is 1.079. So I've incremented the driving constant by a few percent. This is an interesting one. This is period doubling for the pendulum. We saw period doubling for rabbit populations. This is period doubling for the pendulum. Again, you've got in this plot on the right-hand side, you've got a complicated transient where you've got a complicated path and you're looping the loop. And late times, this is what the phase space in the Poincare section point looks like. So on this plot, the phase space trajectory looks like two funny shaped, strange shaped ovals. The phase space trajectory is actually, of course, that you go around one of them, then you go around the other one. So you go around the inner, then you go around the outer to make one complete period. We've got two Poincare section points here. Remember, we're sampling the coordinates, theta and omega of the pendulum every natural period. We find it here. Stairs back, and half the time we find it here, downstairs to the right. So that's further evidence that it's going around one path and then it's going around the other path. Going around the outer, then going around the inner, vice versa. So this is period doubling, because now to complete one period, we have to go around this loop of phase space 2 times. It takes 2 driving periods to complete the complete orbit, which includes the inner and the outer orbit. So you see it very clearly on the Poincare section and the phase space plot. Let's go a little bit further in our driving constant. So let's just add a balance. So we go from 1.079 to 1.80. And if we do that, we see a further bifurcation. That further bifurcation now, look at this is a much expanded angle in theta to show the, again, what we're seeing is periodic motion of the pendulum as we sample it, say, at the driving period, or as we look at it as a function of time. But now we've had another period doubling of the pendulum's motion. We're seeing a much more complicated shape in phase space, theta and omega, that includes looping the loop. And we're seeing, when we're sampling it periodically in the driving period, we see 3 distinct points here. So maybe we've had a period doubling, and then one of those paths that got doubled, it doubled itself. So that might create a period that's 3 times the driving period. And this is again the onset of chaos. And I'm going to swap to another code. So any questions on this code? I mean, you could spend your whole evening or week putting in different numbers for the driving constant or the driving frequency and explore the world of chaotic motion and bifurcation for the damp-driven pendulum. But that's a costly way of doing it with your own time, right? If we want to further, we sort of stuck our toe in the waters of chaos with the damp-driven pendulum, right? Last class with phase space, we just edged down the frequency and we saw the appearance of bifurcation and chaos by choosing a few values of the frequency of the driving force. In this case, again, we just kind of put our toe in the waters of bifurcation and chaos by seeing bifurcation and the transition towards chaos by choosing a few values of the driving constant. If we really want to explore this well, we want to scan the space of the driving constant, vary it systematically. We want to scan, say, the space of the driving frequency, vary it systematically. So I've got a second code here in which I basically do it. And I'm going to scan the driving constant. Let's run all of this. So this is basically the same code as the previous code, except I've added in a loop. And the loop is to vary the driving constant, is to change the driving constant. And I'm going to try change the driving constant from some lower starting driving constant up to some other higher driving constant in some little steps of driving constant. So I'm going to discretely scan the driving constant, and I'm going to plot the results. But what I'm going to do is I'm not going to plot the phase spacing, because if I start plotting the phase spaces for all these different driving constants, it's going to be an overwhelming plot. I'm just going to make a plot of the Poincare section plots, which would typically, if you didn't have bifurcation, they're just 1 point for a given driving constant. Or when we had bifurcation, we had 2 points for a given driving constant. So I'm just going to plot those points on what we're going to call a bifurcation or a Feigenbaum plot. So I want to show you that, and this is basically the homework assignment, or along the lines of the homework assignment. So again, I'm defining the usual functions, defining the constants associated with the pendulum, damp-driven pendulum. All this is the same, except when I get down to, sorry. I'm going to have a loop. I'm going to have a nested loop. I've got one loop when I calculate the solution for a given gamma. That calculates theta and phi from the initial values of theta and phi. I'm going to plug that into another loop that varies the gamma. So that way I can scan gamma and look at the Poincare section points. So this is my initial gamma. This is the solo change in gamma. So I'm going to scan from 1.078 to 1.080. That's the range. That includes the last 2 points I did on the last code, because we did 1.079 and 1.80. And these are the number of steps that I'm going to do it. So I just added that. And the other thing I added was this loop, right? This internal loop here is the one that's finding the solution for a given gamma. And this outer loop is the one that's going to step through the different values of gamma, from the lowest gamma to the highest gamma in these n gamma steps of gamma. So that I added in that one extra loop. So those are the basic changes that I made in the calculation. And then when I make the Feigenbaum plot, or the bifurcation plot, the other change is that my axes are not going to be theta and omega. What I'm going to do is plot the theta Poincare section points vertically and the driving constant horizontal. So it's going to be theta versus driving constant because I'm scanning the driving constant. And it's going to be omega versus driving constant. So I'm going to make this new type of plot, which is my bifurcation or my my Feigenbaum plot. So you see the two plots I'm going to make are the gamma value versus theta. And so gamma is like the independent variable, and theta is the Poincare section theta, and then gamma versus omega. And gamma kind of a dependent variable, the thing I'm deliberately independent variable, I'm deliberately varying that. And these are the thetas of the Poincare section points. And so that's basically the plotting I do. And so let me go to the results. Sorry, this is so small. This is the driving constant horizontal, both of them. Top one is the lost the axis here, but it's theta for the Poincare section points. This one is omega for the Poincare section points. Sometimes you see 2 points. This is where you've got a bifurcation. Sometimes you see 3 points for a given gamma. That's where you've got, we suppose, 2 bifurcations. And so this is the type of plot that will expose the bifurcations. I want to show you so I just ran this code. If you run it for a long time, you can make a much finer division. And I'll just show you this too anyway. Sorry, I know I've overrun terribly. Where's I lost my slides. Just want to show you how this becomes a Poincare section plot. So this is the type of plot I just showed you. Again, horizontally is the driving constant and vertically is either theta or omega. And you see either 1 or 2 or 3 Poincare points or values of theta or values of omega for a certain driving constant. That's bifurcations. If you did it with a much finer time scale, you start to create those things that might be familiar from the rabbit populations or the human populations, where you can really map out how a single orbit bifurcates into a pair of orbits, and then you get for example, an additional bifurcation here. And so that is a traditional Feigenbaum plot. This one here is over a huge space of driving constant from the region that we've worked in this class up until the region of 1.5, where we've seen chaos in the last class.